Welcome to The Explainer. Today, we are embarking on a really epic journey, a true deep dive masterclass into one of the most significant transformations happening in modern technology. We're talking about the telco industry's massive migration from a world of rigid, proprietary hardware to a flexible, open, software-defined future. We're calling this the story of a great migration, and that's not an exaggeration. This is a fundamental shift, not just in the technology they use, but in the entire philosophy, the day-to-day operations, and really the very definition of what a telecommunications company can even be. For decades, you have to remember, the telco world was built on these very specialized, single-purpose boxes that you'd get from just a handful of big vendors. Every single function, whether it was a router, a firewall, a mobile gateway, it was its own physical appliance, it had its own proprietary operating system, its own unique management interface, and what this created was a landscape that was, incredibly stable, for sure, but also incredibly slow to evolve, super expensive to scale, and it left the telcos completely locked into their vendors. The shift we're going to explore today is all about dissolving those boxes into pure software. Software that can run on common, off-the-shelf servers, all orchestrated by the exact same cloud-native principles that power the world's biggest web companies. It's a move from a world of hardware to a world of software. So here is our map for this extensive journey. And we're going to treat this as the really in-depth exploration it deserves. We're going to start at the Telco Crossroads to truly, and I mean truly, understand the deep-seated operational and business crises that forced this monumental change. This wasn't really a choice. It was an absolute necessity. Then we'll establish our cloud-native compass, and we'll define the core architectural principles that are guiding this migration. These are essentially the new rules of the road. With those principles understood, we'll see how they're being applied to what is probably the thorniest part of the whole problem: taming the network itself. From there, we're going to address the immense challenge of scale by looking at the automation assembly line that's required to manage not just one site, but thousands of them, all consistently. After that, we'll push into the Open RAN frontier, which is this ambitious, kind of contentious effort to disaggregate the very last bastion of proprietary hardware, the radio network. And then finally, we'll look at the ultimate challenge, which, you'll see, is way more human than technical: rebuilding the Tower of Babel to create a common language for innovation and value. All right, so to begin our journey, we really have to understand the landscape of the old world. Why was this great migration even necessary? This wasn't a change for the sake of change. It was born out of these deep, systemic problems that were making the traditional telco model more and more unsustainable, especially in an era that's defined by the speed and the flexibility of the cloud. It was really a perfect storm. You had slowing revenue growth, you had skyrocketing operational costs, and then you had this looming threat of the hyperscale cloud providers, who were just totally redefining what customers expected from digital services. The old way of working, of rolling out services, it just couldn't deliver the kind of agility that was needed to compete, let alone innovate. This quote from Guillaume Nevicato at Orange, it just perfectly captures the human side of this entire problem. It's a story he shared that I think resonates with so many engineers. Just imagine this scenario for a second. You're the new person on a team, and on day one, you find out you're responsible for 100 production sites. 100. That is a massive, terrifying responsibility. He says the team is friendly, which is great, right? But their knowledge, the institutional memory, is passed down through what he calls oral tradition. What does that mean? It means all the critical information about how these incredibly complex systems are configured, how they're tweaked, how they're maintained. None of it is written down in a reliable, automated, or verifiable way. It lives in people's heads. It's in old chat logs. It's passed on through verbal instructions during a late-night call. Think about it. Over years, countless small changes, emergency fixes, undocumented tweaks have been made across these 100 sites. So the question he asks becomes a truly terrifying one. How can you possibly guarantee that site number 1 is configured the same way as site number 73? The simple answer is, you can't. This oral tradition creates this constant configuration drift, massive inconsistency, a brittleness where you're afraid to touch anything, and an enormous risk of human error. It's an absolute nightmare for reliability, for security audits, and for any hope you might have of scaling efficiently. Let's put a number on that complexity. 20,000. That is the number of lines of what's called imperative Ansible code that Orange needed to manage the complete lifecycle of just one single use case, a content delivery network, or CDN. Just let that sink in. 20,000 lines of step-by-step instructions telling the system exactly how to do everything. How to provision to virtual machines, how to install the software, how to configure all the network interfaces, how to set up the monitoring, and, crucially, how to perform an upgrade. This isn't just code, it's really a saga of fragility. It's a mountain of procedure. And every single time the underlying infrastructure changed or the application vendor released a patch, this mountain of code had to be meticulously reviewed and updated by experts, the very few people who still understood it. The maintenance overhead was just immense. The system becomes so complex, so bespoke, that it's nearly impossible for any single person to understand it all. And that makes it a huge operational burden. And as we're going to see, the new cloud-native approach, the declarative approach, it reduces this entire thing to less than 1,000 lines of configuration. We're talking about a 95% reduction. That is not an improvement. That is a revolution. It is a true game changer. This slide right here perfectly contrasts the old way with the new philosophy, as it was laid out by Cedric Yahul from Oracle. Let's really break this down. The legacy model on the left was fundamentally imperative. That meant it relied on scripts that gave very specific step-by-step commands. It's like giving a chef a recipe that's 1,000 pages long. It also often required engineers to have direct local access to the machines, and it was built on completely proprietary processes and tools. This created what he calls a supplier tech silo. What that means is each vendor, for your router, your firewall, whatever, brought their own specific, unique tools for managing their piece of the network. This created this deep, painful technical vendor lock-in. If you wanted to change a vendor, you had to rip out not just their physical equipment, but their entire operational tool chain, and then retrain your entire staff. Now, the new GitOps-based model on the right completely flips this paradigm. First, it's declarative. You don't say the steps, you just state what you want the end result to be. I want a pizza with pepperoni, not the recipe for the dough. It's managed remotely through APIs, it's built on open standards, and is therefore completely vendor agnostic. There's no supplier tech silo. Because the idea is everyone agrees to use standard tools from the Cloud Native Computing Foundation, the CNCF. This represents a really fundamental shift in power and responsibility, moving away from these closed, costly, siloed systems to an open, collaborative, and just far more efficient ecosystem. Okay, so having seen the really deep problems of the old world, we now need a compass, something to guide us toward the new one. This migration, it's not just about swapping out old tools for new ones. That would be missing the point entirely. It's about adopting a completely new set of guiding principles. This whole section is about the core philosophy. You could even call it the architectural DNA of the cloud-native approach that makes this entire transformation possible and, more importantly, sustainable. These are the guiding stars for building the new world. So, the true north on our compass, the most important concept, is the Kubernetes Resource Model, or KRM. Now, a lot of people see Kubernetes and they just think it's for orchestrating containers, but its real engine, its secret weapon, is KRM. It's an incredibly flexible, declarative automation framework. At its core, KRM is a universal way to describe a desired state for anything. Using these extensions called custom resource definitions, or CRDs, we can literally teach the Kubernetes API to understand and manage new concepts. We can teach it what a network is, what a physical server is, what an IP address is, or a firewall policy. These CRDs basically define new types of objects, like adding a new word to the dictionary. Then, we can create instances of these as custom resources, or CRs. And the final magic ingredient is the operator, or controller. This is a piece of software, a little robot, that constantly watches for these CRs and contains all the operational logic to make the real world match the desired state you declared in the resource. KRM is the universal language for automation in this new world. Now, a key pattern that's built on top of KRM is the claim model. And this is just a brilliant design pattern. It's already used widely in Kubernetes for things like storage with something called persistent volume claims. Here's how it works. As a user or a developer, you simply claim what you want by declaring your intent. You create a resource that says something like, hey, I need 1 gigabyte of fast storage. Notice what you're not saying. You don't specify how to get it, which specific storage array to use, or what the underlying volume ID should be. The system, through its specialized controllers, figures all of that out for you. This elegantly separates your high-level intent from all the messy, low-level implementation details.
And this abstraction is the absolute key to simplifying tremendously complex tasks and empowering developers to self-serve without needing to be experts in the underlying infrastructure.
This flow right here shows the claim model in beautiful action. The user, the human being, only performs step 1. They define their intent in a configuration file and they commit it to Git. That's it. Their job is done. The rest of this entire flow is a completely automated, non-stop reconciliation loop. So let's just walk through it. First, the stateful set controller inside Kubernetes sees the user's intent. And in step 2, it creates the actual persistent volume claim resource. Now, another specialized controller, the persistent volume controller, sees this new claim pop up. In step 3, it springs into action. It communicates with the underlying storage system, whatever that may be, and it dynamically provisions a real persistent volume. Then in step 4, it binds the claim to that new volume, updating the status of the claim to bound. Finally, the original stateful set controller, which has just been waiting patiently this whole time, sees that the claim is now bound, and it finally proceeds with step 5, creating the application pod, which can now mount its requested storage and start up. This is the magic of Kubernetes. All these independent controllers working together constantly to make the actual state of the world match the desired state that was defined by the user.
This table, which is based on the real-world work and experience of the engineers over at Swisscom, it just crystallizes the benefits of this entire approach. Let's compare what we'll call pure GitOps with GitOps empowered by KRM and the claim model. In a pure GitOps world, the single source of truth is 100% in Git. And that sounds good, but it means every single detail, every single IP address, every VLAN ID, every server serial number, all of it must be defined and stored in Git. This leads to a total lack of abstraction, and it makes the whole system incredibly brittle. If you need a new IP address, someone has to go manually find an available one and then update a Git file. Now, with KRM, the source of truth is actually split. Git holds the high-level intent, the what, while Kubernetes dynamically manages the low-level details, the how. This provides incredible abstraction. It's far more flexible because the system can dynamically assemble the final configuration at runtime. And it's so much easier to scale and operate because you, the human, are managing intent, not a massive sea of complex, interdependent, low-level details.
Okay, we have our principles. We have our compass. Now it's time to apply them to one of the most complex, the most critical, and traditionally the most rigid areas in the entire telco world, the network itself. How do we take these really effective abstract ideas like KRM and the claim model and actually use them to tame the wild, wild world of IP addresses and VLANs and routing protocols and all that specialized network hardware? This is where the rubber truly meets the road. This is such a critical realization that the community came to, and it's really the core thesis of the Kubernetes initiative. While Kubernetes provides this amazing foundational automation framework, that KRM machinery we just talked about, it was never built with the specific, complex needs of telco networking in mind. Out of the box, Kubernetes just lacks native concepts of network topology. It has no idea what that is, it doesn't understand the operational state of a BGP routing session, and its apply and reconcile nature, while it's transformative, it doesn't have the rock-solid guardrails, the transactionality, and the bulletproof change management that critical network infrastructure absolutely positively requires. We can't just cross our fingers and hope for eventual consistency when we're talking about the network. We need guarantees. So the clear conclusion was that we need to extend Kubernetes. So the very first step in automating any complex system is you have to establish a single, authoritative source of truth. You need one place that knows everything. For networking, many in the industry, including teams like Swisscom, are turning to fantastic open-source tools like Netbox. You should think of Netbox as the master database, the grand ledger for the entire network. It handles IP address management, or IPAM, which means it's tracking which IP ranges exist, which ones are available, and which ones have been allocated. It also handles data center infrastructure management, or DCIM, so it's tracking which servers are in which racks, how they're cabled together, and so on. Before you can even dream of automating, you need to know exactly what you have, and Netbox provides that ground truth. And this is where it all connects right back to our cloud-native compass. The Netbox operator is a controller, another one of those little software robots that extends Kubernetes. It basically teaches Kubernetes how to speak Netbox. It builds a bridge between the Kubernetes world of declarative intent and the network source of truth in Netbox. And most importantly, it brings that powerful and effective claim model to the world of networking. So now, an application running inside Kubernetes can simply claim a network resource, like an IP prefix, without needing to know any of the underlying details of how IP addresses are managed. The operator handles the entire life cycle of allocating that resource from Netbox and then making it available right inside the Kubernetes cluster.
Does this look familiar? This flow should feel very, very similar to the storage example we saw just a little bit earlier. It's the exact same declarative reconciliation pattern, but now it's being applied to IP addresses. So in step 1, a developer defines a prefix claim in a Git repository stating their intent. I need a /30 prefix that comes from the parent production network. That's it. The prefix claim controller sees this new claim, and in step 3, it communicates with the Netbox API to find and reserve a suitable available prefix. It then creates a new prefix resource inside Kubernetes that contains the allocated address. This entire process just perfectly demonstrates the power of having a universal declarative model. We've moved from engineers manually editing IP addresses in spreadsheets, which is a recipe for disaster, to a fully automated intent-driven system that ensures consistency. And, as the Swisscom team brilliantly demonstrated, this model even supports sticky IPs, which allows a claimed IP address to be restored to the very same application even after it's been deleted and recreated. That is an absolutely critical feature for many stateful Telco network functions. Okay, so managing IP addresses is one huge part of the puzzle, but what about the actual physical or virtual network interfaces themselves, especially the specialized ones, the ones with fancy capabilities like DPDK or SRIOV? For a long time, the community relied on this whole series of complex, you could even say hacky, plugins and annotations to handle this. But now, the community is converging on a much cleaner native solution called Dynamic Resource Allocation, or DRA. DRA is a new feature in Kubernetes that provides a standardized, built-in way for a pod to request a specific type of resource, like a network interface that has certain capabilities. But more importantly, it integrates directly with the Kubernetes scheduler. This ensures that the pod is only scheduled onto a node that can actually provide that specific resource. This is an absolute game changer for attaching workloads to the specialized, high-performance networks that are so common in the telco world.
All right, so we have the principles. We've got the tools to manage individual network resources in a cloud-native way. That's fantastic. But the telco challenge is one of just massive, mind-boggling scale. We're not managing one cluster here. We're talking about managing hundreds or even thousands of sites. And each one of those sites might have unique configurations, and it's probably going to be composed of software packages from dozens of different vendors. So to manage this staggering complexity, you can't do it by hand. You need an automation assembly line. This is precisely the challenge that these really exciting open source projects like Nefio are designed to solve. And right at the heart of Nefio is a core component called Porch. The best way to think about Porch is as a factory, a software assembly line for creating, composing, and customizing the software packages that will eventually be deployed to those thousands of edge clusters. It is built from the ground up to address the scale problem head-on. Porch does something pretty amazing. It provides a Kubernetes-style API on top of Git repositories. This allows you to programmatically manipulate and manage all of your configuration packages before they're ever deployed. The core process here, a central concept in this Nefio project, is what they call hydration. And it's a fantastic analogy. You start with a dry blueprint package. This is a generic, reusable template for a workload, like, say, a 5G user plane function. It follows the don't repeat yourself, or DRY principle. It contains zero specific information about any single site. It's just the pure template. Then, Porch acts as a controller in our assembly line. It takes this dry blueprint, and it combines it with site-specific data. You know, the unique IP addresses that we got from Netbox, the specific host names for that site, all the local configurations, and it generates thousands of unique wet deployment packages. Each one of these wet packages is a fully specified, fully hydrated instance of the blueprint. It contains all the unique information needed for one particular deployment. And now, it's ready for a standard GitOps tool like Flux or Argo CD to just pick it up and deploy it to its target cluster.
This real-world scenario from the Silva project just shows the automation assembly line in beautiful action. The demo, which comes from an open-source initiative that Orange is heavily involved in, it shows a complete live upgrade of a Kubernetes cluster. And how does this whole thing start? Not with a 200-page manual procedure document, not with a late-night call, but with a simple git commit. An engineer changes just 2 lines of code in a configuration file. They change the operating system and they change the Kubernetes version. That's the intent. That's it. The GitOps engine detects this change and it triggers the automation. Then a project called Cluster API takes over and orchestrates this perfect, graceful rolling upgrade. It brings up a new node with a new configuration, it safely moves the live workloads over, and then it decommissions an old node. It repeats this process one by one until the entire cluster is upgraded. And throughout this whole 30-minute process, the live 5G network function running on the cluster experienced 0 downtime. The key takeaway here, as the presenter stressed, it's not the speed. The speed is cool, but what's really important is the consistency and the reproducibility. There's no manual work, there's no room for human error, there's no oral tradition. There's just a declared intent that the system flawlessly and safely executes.
So we've automated the cloud platform, we've automated the core network functions, we're feeling pretty good. Now we turn our attention to the final, and perhaps the most challenging and contentious frontier in the entire telco world, the radio access network, or the RAN. This is the part of the network that actually connects our phones to the cell towers. And for decades, it has been a monolithic, single-vendor black box. But now, the industry is betting big on a new, disaggregated architecture called Open RAN to finally break it open. The goal of Open RAN is really laudable. They want to diversify the supply chain, increase competition, and drive innovation by allowing operators to mix and match components from all different vendors. Sounds great, right? However, as this industry survey from Spirent clearly shows, this dream creates enormous new challenges. The biggest concern by a huge margin at 40% is multi-vendor interoperability. Just because the interfaces between components are open on paper doesn't mean that components from different vendors will just magically work together perfectly in the real world. Proving this interoperability is a massive, massive undertaking. Following that are concerns about performance and robustness. Can a system you piece together from different parts perform as well as a tightly integrated traditional one? And then, of course, new security overheads, because when you break a single secure box into multiple communicating pieces, you create a much larger attack surface. These are the major hurdles that the industry has to overcome with rigorous automated testing. This right here is the heart of Open RAN. The traditional monolithic base station is broken apart, or disaggregated, into these standardized functional components. You've got the radio unit, or RU, which is the antenna and the radio hardware itself. Then you have the distributed unit, or DU, which sits nearby, and it handles the really real-time, time-sensitive processing. Then there's the centralized unit, or CU, which can be much further away in a data center, and it handles the less time-sensitive functions. And overseeing all of it is the RAN Intelligent Controller, or the RIC. The RIC acts as the brain of the whole thing, running applications that can optimize and automate the network in near real time. The crucial part is that the interfaces between these components, like the open front haul between the RU and the DU, are standardized. In theory, this means an operator could buy an RU from vendor A, a DU from vendor B, and a CU from vendor C. This creates incredible flexibility and choice, but it is also the source of that interoperability nightmare we just saw on the previous slide. So how on earth do you solve this monumental testing challenge? Well, you can't just plug everything in, cross your fingers, and hope for the best. Spirent, who's a leader in network testing, lays out a very clear, methodical, and continuous testing methodology. It's really a 3-step process. First, you perform conformance testing. You test each individual component, the RU, the DU, the CU, completely in isolation, using emulators to simulate its neighbors. This just ensures the component actually conforms to the standards on its own. Next, you move to interoperability testing. Here, you test adjacent pairs of components from different vendors together, so an RU from one vendor with a DU from another. This is where you find all the tricky integration bugs. And then finally, once all the pairs seem to work, you conduct end-to-end performance testing, validating the entire re-aggregated system with realistic, real-world traffic. Now, the most important word on this entire slide is continuous. This whole process has to be fully automated and run constantly. It has to become part of the CI/CD pipeline, and it has to run every single time any vendor pushes a software update to any of their components. All right, we have reached the final part of our journey. We've seen the crisis that prompted this whole migration. We've learned the cloud-native principles that guide it. We've seen the automation tools being built to tame complexity and to handle the scale. But to truly succeed, to unlock all that promised innovation, the industry has to solve a problem that isn't technical at all. It's a human problem. It's a fundamental lack of common understanding. It must find a way to rebuild the proverbial Tower of Babel.
This is such a powerful quote from the architects at Deutsche Telekom, and it gets right to the absolute heart of the matter. The industry chased the promise of disaggregation and softwareization, hoping for this brighter future. But they crashed head-on into a harsh reality. In this new world, the operators, the telcos, were forced to become system integrators. And that's a role they were not prepared for and, frankly, really struggled with. The Tower of Innovation, it started to crumble. And it wasn't because the technology was bad, but because all the different stakeholders, the vendors, the operators, the integrators, they were all effectively speaking different languages. Everyone had their own tools, their own processes, their own interpretations of the standards. There was simply no common understanding of how to work together effectively. So the proposal from Deutsche Telekom to rebuild this tower is not about creating yet another new tool or another new standards body. It's a call for consolidation, for simplification, and for refinement. It's about creating common, machine-readable component manifests. Think of it like a digital user manual for every single piece of software that describes exactly how to configure it, what its dependencies are, and what its capabilities are. It's about agreeing on common infrastructure templates so that a network function can automatically declare what hardware and software it needs in a standard way. It's about defining a best practice CI/CD process and a harmonized lifecycle management model. The ultimate goal is simple but incredibly profound: to get everyone in the entire ecosystem speaking the same language again, to establish a shared foundation of understanding upon which real, rapid innovation can finally be built. And this is the ultimate payoff. This is what becomes possible once all that underlying complexity is tamed by automation and a common understanding is established. The true value of these modernized networks can finally be exposed to the rest of the world through simple, consistent, developer-friendly APIs. And this is the mission of Camera. Camera is an open-source alliance that's working to create a simple abstraction layer over the incredibly complex telco network. So now, a game developer, for example, doesn't need to know what a 5G core quality of service flow is. That's crazy. They can just use a simple Camera API to ask the network for low latency for their gaming traffic. This bridges the vast gap between the arcane world of telecommunications and the massive innovative world of application developers. And Camera is already defining this growing family of really powerful developer-friendly APIs. An application can use simple edge discovery to find the nearest edge cloud to their user, which ensures the lowest possible latency for a responsive application. They could use traffic influence to intelligently route their application's traffic over the network. They could use quality on demand to request guaranteed bandwidth for something like a high-definition video call. They could even use APIs like energy footprint notification to monitor the sustainability and the carbon footprint of their service. These APIs unlock the unique capabilities of the telco network, its geographic reach, its quality of service, its security, and they make them available as simple building blocks for any developer in the world to use.
So our great migration concludes right here. We've journeyed all the way from the brittle, proprietary, hardware-centric past to a future that is declarative, it's automated, and it's open. We've seen that the foundation for this new world is being laid brick by digital brick through the incredibly hard work of countless engineers across a really vibrant ecosystem. It's a transformation that's built on open source, on deep collaboration, and on the painstaking effort to forge a new common understanding. And this journey leaves us with one final, very exciting thought. We have seen the blueprints. The tools are being built. The question is no longer if this will happen. It's happening. The real question is how quickly and how effectively the entire ecosystem can come together to build it, and what truly incredible, maybe even unimaginable new innovations will this robust new foundation ultimately unlock for all of us.